And the problem is, like, I wanted to make clear for everyone what we are talking about. So for example, this is one of the charts that has been shared the most. And the problem with this chart is not that it compares countries that cannot really be compared between each other. That's not really the main issue. The main issue is that it compares numbers that we do not know if they are real or not, if they represent real things or not. So for example, we have two issues with this chart. The first one is undercounting. So the chart is showing the number of deaths due to the virus. But on the other side, there is a lot of evidence that says that those deaths have been undercounted. For example, I've been shared on my newsletter, pandemic.substack.com, evidence that France, Spain, and Italy have been undercounting the number of deaths. So why are we looking at this chart if we know that the numbers are not correct? Not only it is useless, but it's also very dangerous, because we might take decisions based on this chart. Our policymakers might take decisions based on this chart. And if the information they're taking decision on is incorrect, then they will take incorrect decisions. And we really want to avoid this. Another problem is that population size. I had many people asking me, how come that we are comparing, how come that we are comparing countries with different population? Okay, this is not much a problem, because population only comes in during saturation. So for example, two countries that have one single outbreak, let's say the US, very big, large country, and Switzerland, very small country, they will have the same number of contagions for the first weeks until we start to incur problems like saturation. So like everyone in Switzerland, or most of people in Switzerland, they are infected. Then we began reaching a roof of saturation, a roof in the number of cases. But before that, there will be no difference between the number of cases and the number of deaths in a small country and in a big country. So from this point of view, it is correct to make this comparison. But the point on population does not really matter. The point which really matters is undercounting. So we know that at least some of the data in this chart is wrong because of undercounting. We do not know by how much. So this makes the chart completely useless. And we should fully disregard. It's not just because it contains some data, then it might be somehow useless. No, unless all the data contained in a chart is completely correct, then the chart will give us wrong data. So this is the theme for today's call, is how to understand whether the data that we're using is correct or not, and to understand that if the data is incorrect, then we should simply completely forget about the thing that we are looking at, even if we think that it might provide some data. I will now go a bit deeper in the topic of undercounting. We have two problems. The first problem is that we know that we are undercounting in at least some countries, but we do not know by how much. So we do not know if the real number of deaths is 50% more, if it's double more, or if it's 4 times as much. And the second problem, so we also do not know what's the uncertainty on the multiplier on how much we are undercounting. And those two things together, they make so that our data is completely useless. I make another example. every time that you have a distribution and you're sampling parts of this distribution, you have at least two sources of uncertainty. The first source is that you take a sample, you analyze these samples, so maybe you have an average. There is no guarantee that in the future, the average of the next sample will be the same of the average of the previous sample. And then the second source of uncertainty is that there is no guarantee that the sample that you took was representative of the underlying distribution. So in this case of counting deaths, we have two problems. The first problem is that even if we make a precise measure of how many people are dying, we have no idea on how many people will die in 1 week. So we do not know if it's going to be the same number, if it's going to be more, if it's going to be less. And the second problem is that we do not know even the number that we have that is theoretically would represent the past. We do not know if it actually represents the past or not. So unless we know those two things, we should fully disregard the measure that we are making. And I've been writing a post about this today on scientism that I published on pandemic.substack.com. All those charts that are made, like this chart, that are made on data which is incorrect, they only serve a ritualistic purpose. So because of what we've been taught in school, or because it's what's been rewarded at work or in academia, we have this idea that we are supposed to make charts. We get some data and then we are supposed to make charts to make sense of this data. It almost became a ritual. But this ritual, it does not really have a function if the data is incorrect. It only has the ritual of the function of showing that the person who makes the chart is able to make charts. But that doesn't mean that the person who makes chart is also able to take conclusions which make sense. If you have any questions on what I'm saying, just write to me on Twitter. You can write me a private message. Every few slides, I will just check my private message on Twitter, and if I read any question, I will answer it. The next point I want to touch is about correlation. So there has been this chart from a study that shows that there is some correlation between temperature on the x-axis and between the R, which is a measure of how many people a contagious person will be able to infect on the y-axis. And the study says that there is some correlation. And they say so because they have plotted some data points, and then they've run a regression, and the regression shows a line. And so they think that there is a meaningful correlation. But in this case, I think that most of this correlation is actually bullshit. I have this quote on the left that explains the point very clearly. It says that unless you can handle a line through data without feeling like an idiot, then you should forget about regression analysis. And here, honestly, in this chart, I would feel like an idiot to draw a line if I couldn't see the red line and I only saw the blue dots. Another nice test to know whether you can perform a regression analysis or not is, sorry, 1 second. Okay, a test that you can run to know whether you can run a regression or not is that you take a random point on the y-axis. So for example, on the x-axis. So for example, I'm telling you, there is one more data point on this chart that we are about to add, and the temperature is 5 degrees. Can you know with any good degree of confidence the y of the data point. Looking at this chart, I have no idea whether the R will be 1 or will be 4 or will be anything comprised into that. And so that's a good test that shows that every regression, every correlation that we will try to see from this chart will be mostly meaningless. So whenever you see a scatter plot like this, that's not a good sign for correlation. Usually a scatter plot that has a meaningful correlation almost looks like a line. And this is extremely important, especially if you are a smart person, because the smarter you are on average, the more you will be able to see patterns in noise. And the more you will think that there are correlations when there aren't, and the more you will think that you're making meaningful models out of it. And so paradoxically, the smarter you are, you need to remember that the more rigorous you have to be. I'm just checking Twitter because I've seen that someone posted a question. It's Nacho, thank you. Yes, Nacho is saying, the regression analysis that I showed is bullshit, but perhaps there is a relationship between temperature and humidity and contagion. I have this other chart over here with which I hope to answer Nacho's question. Whenever you see this chart, and the commentary between this chart is that the zone at risk for significant community spread in the near term includes land areas within the green band. Does it make sense or not? So it is true that the biggest transmission cluster took place in the green band. I'm thinking about Spain, China, South Korea, Italy and France, and Iran, and now New York, for example. But what does this chart show us? It only shows us that that the data that we have shows contagion into the green lines. But there are other possible explanations for the green lines. I'm making some example. For example, it could show us not the correlation between temperature and contagion, but between temperature and testing. For example, it might be that countries which are not in the green line, they are not testing enough. We have some evidence, for example, from Indonesia, from the Philippines, from Egypt, that a lot of people that have been visiting those countries and then came back home, they tested positive afterwards. So that could be a sign that those countries are under testing, and so this would invalidate the hypothesis. Another hypothesis is that in the red line, the red areas, they are known for malaria. And so perhaps what's the relationship is not between temperature and virus spread, but there might be some underlying genetic correlation between genetic resistance to malaria and genetic resistance to the coronavirus. I'm not saying that those hypotheses are correct. I'm just saying that this chart alone might point to multiple correlations. And it's very important to, whenever you make some correlation analysis, to understand that it's not because you've seen a correlation with something that that correlation also means causation. This is pretty evident, but I've seen a lot of people on Twitter and in other places pushing theories that only show correlation and not causation, which is fine if you push them in an hypothetical point of view, like that's a possibility that warrants more studies, but it's not fine if you push them as complete evidence. I will pause 2 more seconds to check if there are any more questions. Okay, so I go back a few slides. So the point that I wanted to make is that with the previous charts is that data quality is extremely important. And I'm referring mostly to this chart because this chart is a great analysis on terrible data, and that invalidates the full analysis. So we should spend much more time on to focus on data quality and much less time on analyzing the content of the data, because any analysis that we make on data which is wrong is wrong itself, and the consequences might be dangerous. And so sometimes my students, they ask me like, Luca, how much time should I spend on making sure that data quality is right and on making sure that the analysis are right? And the answers, of course, if we had an ideal world in which we have all the time that we want, will be as much time as needed. But in the real world in which the time is limited and we must prioritize, the answer is it depends on what's the consequences that will come out of the analysis. If there is a chance that a wrong analysis will have disastrous consequences, then you should spend a lot of time in validating the data and validating the analysis that you make on the data. If instead there are not much consequences from the study being wrong, then it's much more okay to make to jump to quicker conclusions. But then, of course, you should make clear that those conclusions are like preliminary and they only warrant more research. But then you should be very careful, because there are a lot of times cases in which the scientists make a research, it publishes the conclusion saying that they are very preliminary, and then the press or some policymakers, they take the study, they take the conclusions, and they leave out the part regarding the fact that the conclusions are preliminary. And then they take huge policy decisions out of it. So the thing is, be very careful with your studies and with the conclusions of those studies. So especially if your study has a conclusion that could invite people to take more risks out of it, then you need to spend extra time on making sure that the data is correct and that the analysis is correct, and not only on the analysis, which is what most peer reviewers are doing. I've just seen that a couple of months ago there has been this study in which some peer reviewers he actually asked to see the raw data that was behind the paper that was submitted. So usually what happens is that a lot of times people submit a paper to peer reviewers, and the peer reviewers is focused on checking that the analysis is correct based on the data, but they do not check that the data is actually true. And the result of this study was that, I don't remember the exact numbers, but I think that in almost half of the cases in which the peer reviewer was asking to see the raw data or was asking questions about the raw data, then either the raw data was not provided or the author will just retract the paper. So it's extremely important that we check data quality. So in this case, again, I come back on this chart. I don't really care about how the chart is made and what the chart is doing if I already know that the data is wrong. I made a similar analysis on Twitter, and someone replied with, yeah, Luca, you pointed one mistake, but the rest of the paper is correct. There is no such thing for two reasons. The first reason is that if the underlying data is wrong, then you can already reject the paper and reject the study without even check at anything else, because it's a bit like in a boat. Once you find a hole in the boat, you know that the boat will sink. You do not need to complete the inspection of the rest of the boat. And then the second thing is that usually our red flags cluster. Usually you have some people which are extremely rigorous and other people which are not rigorous at all, and they only publish studies for ritualistic purpose or because they have a point to make, and first they want to make the point and then they look for data that supports it. And so I'm not saying that if you don't see red flags at the beginning in the data quality, you will not find red flags in the data analysis. But what I'm saying is that usually if you find red flags in the data quality, it's very, very likely that you will find also red flags later on in the data analysis. And then I want to make this point that statistics in the textbook are subordinate to statistics outside the textbook. And here I'm talking about this fact of, there is actually a name, it's called the ludic fallacy. And it's a fallacy in which we are used by statistic courses at university or in high school and textbook exercises in which you are provided some data, and the data is assumed to be correct, and then you are tasked with producing analysis on this data. And then you are evaluated on whether the analysis is right or wrong, but you never check the conditions at the border. And this is called the ludic fallacy because ludic is the Roman word for ludus, game. And in games, usually you already know everything. You know what are the odds, you know the rules of the games, you know how success is measured, and then playing the game right is only it's only about optimization. But in real life, instead, you do not know the rules of the game, you do not know whether the data is correct, you do not know the odds, and you don't even really know how to measure success. And the ludic fallacy is assuming that we are living in a game and we can completely forgot those conditions at the border. And one of those conditions at the border is actually the quality of the data. And so, for example, here I want to show like what in my eyes is science. So in science, you're making some measurements on a reality. And then on the results of the measurement, you make some data analysis. And then maybe you produce a model. And then before you can claim that the model is correct, you need to make sure that it makes sense in reality. And then you will have some feedback. And then the feedback must inform everything that you've made so far. And this is actually what's science. And textbook statistics usually only covers one part of it, and it assumes that everything else is already taken care of. But that's not a real life, and that's not science. I will just check Twitter again if anyone has any questions so far. I will just give you like 30 seconds to write me questions on Twitter. Okay. There's been a question regarding humidity. I will just go back to this chart. So I'm asked, what would it be accurate if questions, if charts like these, they only showed information by percentage of humidity and COVID mortality inside the country and the season? I will answer this. I will answer this question a bit later because there is some concepts I want to pass first. Okay, there is another problem with all these analysis on mortalities that I've seen. I've seen those charts that show mortality by age. And for example, you see that young people, they have this mortality which is much lower than 1%, and then mortality goes up very fast as you progress with age, and then people above 80 or 85, they have 15% mortality about. My problem with this kind of stats is that they only measure direct mortality. I also have other problems, but one of the problems I have with those stats is that they only measure direct mortality. Instead, there are many indirect effects from COVID on how many people die. So, for example, there are not only people that die of COVID because they got COVID, because their lungs got damaged and then there are complications and then they die, but there are also problems, for example, people that have a health condition which is completely uncorrelated. They have a heart attack without ever having been healed of COVID, and then in a normal world they would go to the urgencies and they would be saved, but because the COVID is clogging the urgencies and there are no free ambulances and the doctors are overloaded, they do not get the cure and the treatment that they would get otherwise, and they die. So it's false, for example, to think that mortality of COVID is only the number of people that died because of COVID divided by the number of people which are infected. That's true only for first order mortality, but there are many other people that are dying because of COVID. So, for example, I made this analysis that you can find on pandemic.substack.com, in which to know how many people are actually dying of COVID in Italy, I go to check for some cities how many people are dying in total this March compared to March previous year. So this analysis is very solid, this kind of analysis, because it does not rely on testing procedures, on diagnostic criteria. It does not rely, for example, on making sure that everyone who died of COVID is tested. It doesn't rely on knowing for the denominator of mortality that we know the real number of cases. It doesn't rely on different policies that governments might have on classifying COVID deaths. It doesn't rely on questions like, did he die from the virus or with the virus? It simply checks how many deaths we would expect in a normal year, how many deaths we have this year in which there is also COVID, and it makes the difference. Then, of course, there might be some problems like what if this year there is a high mortality because of two reasons, because of COVID and because maybe there is a bad year for flu. Of course, it's possible, but what you can make then is analysis to see how much is a big year for flu. And you will see that in a big year for flu, maybe there is the multiplier of deaths is 1.5, maybe it's 2, but it's very unlikely that it gets as high as I can read in the table 8.3, for example. And then again, you can just check with reality. You can just check in reality what's the situation in the hospitals, and you can see that they're overloaded. And that already is a great data point that if you have some data, and the data is telling you that not many people are dying, and then you go check the newspapers and you see that people are actually dying, then you know that most probably there is a mistake in your data. Like, you should always consider that if your model and reality are saying two different things, chances are that the reality is the one which is right, and you should double check and triple check your model. But then another commentary that I took is that I had regarding this chart is that this chart only has data for 9 cities. And of course, there are like thousands of cities in Italy. The reason why it has data from few cities is because there is no centralized data source, and I had to manually go and dig the data for every one of these cities, and it's extremely time consuming. Now I want to dispel this idea that more data is always better. This is not necessarily true. Because if you have more data, but all the sample has the same bias, then you will not produce better results, because all the results, they will still have the same bias. I'm making an example. Let's say that China is undercounting mortality. If you have data from 10 cities in China, or if you have data from 1,000 cities in China, and the problem with data is that China is undercounting mortality, having more data will not solve the underlying problem in data quality. So there is this false belief that having more data solves problems in data quality, and this is just wrong. More data solves problems only if you know for sure that there is no common bias across the data. Then, of course, we can ask the question, what is the common bias that those 9 cities in my analysis they have? So one is that they are all in Northern Italy. So of course, it means that my analysis is only valid for Northern Italy. The second thing is that the reason why I chose these cities is because those cities have been on the newspaper for the excess number of deaths. So this chart, this analysis will not be valid to say, oh, coronavirus is causing 5 times the number of deaths in Italy. And if official data says otherwise, then we are undercounting data by 5 times. No, it just means that in a city which is badly hit, then mortality can get as high as 5 times as normal in a given period of time compared to a normal period of time of the same length. So the thing is that you should be very aware of what are the criteria and the biases with whom you selected the data. And then you must know that you should transfer those criteria and those biases to the results. So saying we have these results with this bias and with this data, and you should hopefully say it in the same sentence so that people cannot cherry pick it. And you should know that having more data on the temporal point of view, on the sample size point of view, will not remove any of those biases and of those selection criteria. So yeah, this is the points that I was saying before. If data points in a sample are subject to the same bias, having larger samples will not reduce the bias. So this is the problem that I had with all the analyses that we had in January, which were on the coronavirus, which were based almost exclusively on data coming from China. So I'm not saying that it's wrong to make analysis, because of course we want to have at least some data. And if that's the data that we have, all the data that we have, then it's okay to make some analysis on the data. But then we should know that those conclusions, they do not necessarily tell us only about the virus, but they also tell us about the sample. So in this case, all the analyses that were made on the coronavirus in January, they are telling us as much about the virus as about China. Or actually, we don't even know if it's 50-50. Maybe they're telling us nothing about the virus and everything about China. And there is a name to this phenomenon. It's called the Wittgenstein's ruler. And that's the principle that if you have a ruler, and if you're using a ruler to measure a table, and the ruler is not very precise, then you might as well be using the ruler to measure the table, or the table to measure the ruler. And the formal formulation, or at least my formal formulation about Wittgenstein's ruler, is that the more free parameters you have, the less you know what you are measuring. And so, for example, if the precision of your tool is a free parameter, so you don't know how precise is your tool, or if the sample that you're using is a free parameter, or if the bias that you're using in the sample is a free parameter, so something that you do not know and that you have to estimate, and you're trying to estimate it in the same measure, in the same studies, then the less you know what the study is about. So for example, all the studies that were made in January regarding the virus, they might have been the studies about the coronavirus, or that they could have been studies about China, for example. Or they could have been studies about how people make studies about viruses. I will stop 1 second to check if there is any question. Okay, I check if there is any question on Twitter. Okay. I will continue with talking about averages. There is this problem that I've seen that a lot of people are talking about the average mortality in Italy, for example. But the point is that the mortality in Lombardy is very different from the mortality in Italy. So for example, I think like, I'm just going with memory, so I might be wrong, but I think that mortality in Italy is about 8%. But actually, if you separate it between Lombardy and the rest of Italy, you get something like 12% and 4%. I don't know if the numbers are correct, I'm going by memory, but the point is like, the average about Italy is not telling us very much. It's much more important to know, for example, that Italy has one mortality and Lombardy has another mortality, because if you're thinking about the average in Italy, then you're thinking something like, oh, why there must be something about Italy that makes mortality very high. But then if you realize that mortality in Italy is, in the rest of Italy is kind of average, a bit higher, but still not so different from other countries, but mortality in Lombardy is extremely high, then you begin asking different questions and you begin looking in different points. And then again, you can see that the situation in Bergamo is very different from the situation in Lombardy as a whole. And the basic rule is that you can only average in linear contexts. In linear context, I mean you can only average in places where there is some kind of linear additivity, and also where samples are distributed uniformly along the territory. And about the territory, I mean the spatial territory, I mean the geographical territory. So I should just add one more point to the third bullet point. I take this this chart. That's from the study that was claiming that 50 or 60% of the population in the US is already infected as of last week. I think that there were a couple of problems with this study. One of the problems is that the curve is extremely smooth. You can see the green curves and the brown curves, they're all extremely smooth. Why is it a problem? The problem is that here, the researchers are trying to model what would happen if there were an outbreak in the UK. But the UK is not uniform. London is extremely different from rural Scotland, for example. So a good question that you can ask yourself is, how would the contagion curve look like if the outbreak started in London? So probably you would have a very, very fast rise in the number of cases. And then it will probably continue as a smooth curve, because you could assume that a lot of people are traveling to London and out of London, so the contagion will spread very fast to the rest of Britain, of Great Britain. But how will the curve look like instead if patient 0 were in a rural village in Scotland, for example? The curve would be fast in the beginning, as the little town gets contagious, but then it will be quite flat for a bit, as the virus will struggle to get out of the little town, and then maybe it will get to, let's say, Edinburgh, and then it will grow, but then it will grow not much fast until the point in which the first people, they get to London and they infect people in London, and then it will begin to look the second part of the curve, like the curve that we were analyzing in the first scenario. So my point is, if there are different conditions, if the outbreak will look very different, if patient 1 were in London or were in rural Scotland, then you cannot make a model that averages it out all in the UK. So whenever you have path dependency, so path dependency is the concept that depending on how it started and where it goes, then you have different final results. Then you cannot make forecasts or models which simply assume that the population is uniform and that you can just make use stuff like expected value or assume average distributions, or use stuff like average R0. This is another point about R0. R0 is this constant which measures, which estimates how many people would one person with the virus infect in a population which is unprotected. And of course, R0 is not a property of the virus only, but it's a property of the virus, of the spreader, of the behavior of the spreaders, of the behavior of the population, whether the population has PPEs, whether it's observing social distancing, and so on. And of course, those characteristics, they're not equally spread across the population. So we cannot, again, assume that R0 has an average value and just throw it in our models. And here we go into this fallacy that I call the modelist's fallacy, which says that I build a model that sometimes researchers use, which is they build a model because they want to get data about something that they cannot measure in reality. But then they use data from somewhere else, which itself suffers the same fallacy that you can measure. So for example, in this study from Oxford, the problem was I cannot measure how many people have the virus in the UK. Or, I mean, we could measure it if we made a mass serological test, but apparently we're not ready yet. So the researchers, they were taking data from Italy and plug it in their model to estimate what will happen in the UK. But the problem is that in Italy itself, we do not know if the official numbers are correct or not. So you cannot say official numbers in the UK might be wrong, so let's use official numbers from Italy to predict the official numbers in the UK, because of course you do not even know if the official numbers in Italy are right. I will stop again a couple of seconds just to check if there is any question. So I will check the chat here. Oh yes, hi Teresia. Check if there is any question here on Twitter. They say there's a question, would more of your style data be useful worldwide? Yes, definitely. The problem is not much that my style would be useful, is that the other style, it's harmful. what I want to say is that, like, if you know the data that you have is faulty, then you can take policies just by observing a reality or by observing what works, forgetting about models and forgetting about data. The problem is when you think that your data is correct and your models are correct, and then you might make decisions which are wrong. There was this. So this of course is taken from Taleb's approach. There is this this concept that I read on Twitter, that they are saying, oh, the reason why people didn't understand the importance of the virus and of the epidemic was because people are not used to exponential curves, and they didn't understand how fast the epidemic might grow. And partially it's true, but the thing is, that's not a failure in understanding exponential. It's a failure in basic human empathy, because even someone who doesn't understand exponential could just have looked at what was happening in China or what was happening in Italy, seeing that the hospitals, seeing that the hospitals are full, and understand that something terrible is going on, and you should do something in your own country, and you should do everything you can to avoid the outbreak. And I think that it's so the failure is not in not having the good models. The failure is in understanding that no matter the models, first you should protect yourselves, and then only afterwards, when you're safe, you can afford the time to create models. I will just check if there are any more questions. Nacho, can you please clarify the question? Thank you. I will add one last concept. This should be the last concept for this call. That's the concept of leading indicator and lagging indicators. So this that you can see here is a thing called the pyramid of risk. And the idea is that for any death that you have, you tend to have a lot of ICU patients. But then, of course, there are also a lot of people that are dying without going through the ICU. They die in their homes. But let's just continue with them with this. Then it doesn't matter, because this is, I won't take any conclusions out of it. So that's why I'm saying, like, it shouldn't have to be formally true. Then for each ICU patient, you have a lot of confirmed cases. For each confirmed case, usually you have a lot of suspected cases. And for each suspected case, you have a lot of people who are susceptible to have been infected. So for example, people not wearing the PPEs. The problem is that usually when you have such a pyramid of harm, what you notice is that the top of the pyramid is made of lagging indicators. So indicators that only show you how bad was the past, that only show you like what happened in the past. So for example, the number of deaths, unfortunately, you can only have it after people are dead. The number of ICU patients, you can only have after people get into the ICU, but you still have it a bit before the deaths. And so on, the confirmed cases, suspected cases, and people not wearing PPEs. People not wearing PPEs is a good leading indicator, because you can already know that your population is vulnerable and there will be a lot of deaths if you do not change something, just because you know that there is an epidemic and you see that people in your country are not observing social distancing and they are not wearing masks. So this is, for example, one of the reasons why even when there were an extremely low number of cases, I was predicting in Spain and in France I was predicting a very high number of deaths. My reasoning was very simple. I wasn't looking at the number of cases in Spain and France. I wasn't looking at the number of deaths. I was just thinking there is an outbreak and those populations are still behaving as normal, so there will naturally be a lot of deaths. And this is a much, much more solid approach than charting how many people you have in the ICU, how many deaths you have, and to try to extrapolate some trend out of it. And the problem with those trends is that because you're measuring lagging indicators, those are trends with data from the past that will only predict the past. They assume that the future will look like the past, but you have no guarantee of that. Instead, if you measure leading indicators, you are much more sure that changes in leading indicators, they will affect the future. So for example, if you take the lagging indicator of deaths, I think that right now you have kind of similar number of deaths in Italy and in the US. Sorry, in Italy and in Spain, I meant. And you could say that based on that, that you could expect a similar number of deaths in the both countries in 1 year. But I think that there will be much more deaths in Spain instead, because then if you look at leading indicators, Italy began social distancing a bit earlier. So that's what I mean by leading indicators. They tend to have much more predictive power than lagging indicators. So they are much more important to measure, even if in the headlines, you only tend to see the lagging indicators, the number of deaths. Then you also have a couple more advantages in measuring leading indicators. So the first one is that the size of the sample. So I've said before that you have many less deaths, which are at the top of the pyramid, than people not wearing PPEs. So it means that the numbers that you measure at the top will be very volatile, and the number that you measure at the bottom will tend to be more stable. So usually when I'm consulting manufacturing plants on workplace safety, what I'm telling them is like, if you measure the number of deaths and you see a trend, for example, last year there was, 2 years ago, there was 1 person who died, last year 1 person who died, and this year 0 people died, you cannot really know whether your plant is becoming safer or not, because the sample is too small, and you do not know if this year you have 0 deaths because the plant got safer, or because just because of random volatility. Instead, if you measure the base of the pyramid, for example, the number of people which are not wearing the safety helmet, in this case, you have a much larger sample. So if you know that last year, that 2 years ago, 10% of people were wearing the helmet, last year 20% of people, and this year 90% of people, then the samples are large enough to say that yes, the plant is getting safer. And then the other advantage of using a leading indicator is that leading indicators are proactive, whereas lagging indicators are reactive, as you can see at the rightmost part of the chart. The problem with deaths is that once they happen, if you realize that you made a mistake, then before you change it, you will have more deaths. Instead, if you measure the bottom of the pyramid, the leading indicators, you can understand that things are going wrong before you actually have the consequences, before the consequence materialize. So for example, how can we measure if a lockdown is working? If we only look at the number of deaths, and after 2 weeks, we realize that the number of deaths is not trending down, then we realize that we made a mistake and we need a stricter lockdown, for example. Then we lost 2 weeks of time and we lost the lives of a lot of people. If instead we measure social contact, so for example, we take a sample of the population and we measure how many people those people are having contact with, and we see that during a lockdown, this number is going down, and then we see, for example, that it's going down, but not as much as we expected, then we can already know from day 2 that the lockdown is not working, and we can already implement changes without waiting for 12 more days of deaths. So that's why I would like to invite everyone, when we have such whenever you can draw this kind of pyramid of harm or pyramid of risk, to always prefer metrics that are at the basis of the pyramid rather than metrics that are on the top. Of course, it doesn't mean that we should completely neglect the top, or that analyses that make the top, that check the top, are useless. What it means is that okay, so we were talking about how about what indicators to use for the lockdown. So, for example, we want to know what are the good metrics that we can use both to optimize the lockdown, so to adapt it, so that we can know whether it's working, whether it's not working, whether we have to change something, and also to have an idea of how long will the lockdown need to be. So first of all, we need to know, like, what is a lockdown for? The first thing to consider is, so the lockdown is for preventing the contagion to spread further. But not only, it's also to make sure that we isolate the sick, that we know all the people who are the sick, and either we let them out of their apartment only when they will not be able to infect anyone, or we move them to some special isolation or quarantine area. So this tells us that the lockdown does not end when the curve of death or the curve of contagion begins trending down. The lockdown ends the moment that we know who are the sick and who are not the sick, and we manage to isolate the first group, or to make sure that they cannot anyway contage anyone else. So I find idiotic that right now, at least in Italy, one of the metrics that we are looking to know whether the lockdown, how long it will still be, is the number of contagions. Because if the number of contagions trends down, but we still do not know who are the people who are sick, then the lockdown will have to continue until the number of new cases is 0. Which, of course, it's a possibility, it's a strategy. But then we also need to understand that there's going to be a lot of time before the number of new cases goes to 0. Because not only are people infect people outside of the house, but they also infect people inside the house. So we want to have indicators that measure the thing that matters for the lockdown. And the thing that matters for the lockdown is knowing who are the sick people, which people are infected. And so the indicators that we want to use is how many people we are testing, what is our testing capacity, for example. And then again, how many people we're testing, it matters which ones. Because if we are only testing people when they come to the hospital, we do not know how many sick people there are in the houses. And we do not know how many asymptomatics have the virus. So what matters for the lockdown is how many tests are made door to door. So that we can go to an apartment, for example, test the 3 or 4 people living there, and then being sure that in that apartment there is not the virus. And then if we do it for all the apartment block, and if we do it for all the block, for all the neighborhood, and we do for all the city, then at this point we can say we can lift the lockdown from the city. Otherwise, the lockdown needs to be at least 5 weeks, as Yanir Baryam and Nassim Nicholas Taleb pointed out in their videos. Why 5 weeks? Because we need 2 weeks for the infected that got the virus inside an apartment to develop symptoms and infect the rest of the family, 2 more weeks for the rest of the family to develop symptoms, and then 1 more week of safety cushion. And only after those 5 weeks, if a family didn't get sick, you can know that this family will not get sick in the future, unless it gets into contact with people from outside. So the thing is, for the lockdown, you basically have 2 options. Either you accept that the lockdown will last at least 5 weeks. And in this case, it has to be a very strict lockdown, because you cannot afford the fact that people get infected, for example, going to buy groceries or going to work. And then or you need to use testing and isolation. And in this case, the indicators that you want to use are the indicators that measure how well you're doing the door-to-door testing and how well you're doing the isolation. And then, of course, it makes no sense to measure them on an average across the country, because what will happen most likely is that just as some countries, they began having lockdowns in one city or in one region, the so-called red zones, and then they only later on they put the lockdown all over the country. What is likely is that the lockdown will end on a region-to-region basis, on a state-to-state basis, or on a city-to-city basis. Why? Because, sorry. Because you cannot test everyone in the city, everyone in the country at the same time. It's much easier to test one city, declare it virus-free, and then release the lockdown from there, keep the borders very strict so that you don't get people from the other zones get in, and then go to the next city, and so on. So you want to measure those indicators on a city-to-city basis, if you go with the assumption that the lockdown will be released on a city-to-city basis. So do not use averages across the country. Okay, that would be it from my side, because I plan to keep it only 1 hour long. Now it's more because of the power cut. I will check once more if there is any question on Twitter or in the group chat. Okay, I have this question. Just assume, talking about mortality data. So we are back to we're basically back to this slide. What happens if you're constantly wrong? Ask the question. So for example, what happens if you know that the data grossly undercounts, but has been taken in consistently across hospitals, and I imagine even across countries, for example? My opinion is that the chart is still useless, because I cannot fathom how you can know that the data is undercounting, but it's doing it, and you don't know by how much, but you know that it's doing it on a consistent basis. Because, for example, yeah, you can have, for example, some tests with, let's say, random number, 10% false negatives, and so you can know that even if you test everyone, you will undercount by 10%. But that's not what we're talking about here, because if that was the case, you just multiply everything by, you divide everything by 90%, and you get to the real number. The problem usually is that when you're undercounting or when you have data problems, you also do not know the extent of the data problem. You know that you have a data problem, but you do not know the extent, because otherwise, usually, you would solve the data problem. So yeah, it's extremely difficult to know that you're consistently measuring wrong, but with the same consistent error. That's very, very unlikely. I'll check if there is any other question from the chat. Will I share a recording? Yes, I will share the recording, assuming that my power cut didn't create any problem with the recording. Otherwise, I will record a second, I will make a second recording later on, and then I will share that one. Then there is another question. Do I have a sense of what kind of protocols were used for testing in China? It is my understanding that what they did is that they went door to door, screening the temperature of everyone multiple times, and they did it for long enough that they could check that no one was infected. So to give you an idea, the 5 weeks lockdown is the hypothesis in which you do not do door-to-door screening, because you need to make sure that you can only know that an apartment is free from the virus if you give time for the first patient in the apartment to become infective, to infect the other people, and for the other people to develop symptoms. But instead, if you measure temperatures, you can cut this time. That's so measuring temperature door to door. I know that it was one of the part of the protocol. I also know that it's not the full protocol. I know that the WHO released a report on that. Of course, we all know that the WHO has been very problematic with its recommendations. So I'm not saying that the report can be considered neither fully exhaustive, but I do think that there will be some good learnings in that. Then I have another question. On Twitter. Does it mean that almost none of the data out there, let's say on COVID, is usable? Each come with a different context, so we cannot compare and extrapolate across different countries, for example. I think that's largely correct, unless you have reasons to think that the same bias will apply to the other countries as well. So that's why I was saying before that you need to know what's the bias that you have in your data. So I'm making an example. I'm making a few examples. So for example, a clinical study on a drug on some patients in China is quite likely to replicate on patients outside of China, because I cannot really think of too many biases out there that would apply. There might be some genetics that you want to double check, because maybe there could be something over that, but still you can be quite reliable on that. Conversely, for example, data on the mortality of Bergamo, so the very high mortality of Bergamo. So we need to be aware that it's not mortality from the coronavirus only. It's representative of mortality from the coronavirus in a healthcare system that is overloaded. So for example, you shouldn't use the data to extrapolate it to other countries in general, but you can use the data to extrapolate it to other countries under the condition that they're going to be overwhelmed by healthcare. Or what you can do even better is to take the difference between what's the mortality in Italy with overwhelming and mortality in regions in Italy without the overwhelming of the healthcare system, and take the difference and imagine that it will apply to your country as well, up to a certain limit. But then again, even these kind of considerations will not be very exact. So my best criteria is, would use this data lead me to take more risks or lead me to take more precautions? If the answer is to take more precautions, then I'm much more likely to say use it because the downside is lower. Whereas instead, if the data will take you to take more risks, in this case, I will tell you, like, be extremely careful and probably better not to use it because better be safe than sorry, especially under conditions like epidemics, like climate change, in which the precautionary principle applies. Then more questions. So yeah, so just to finish this. So the problem is, like, how can a country which is still lucky enough to be still in an early stage of the epidemics use data from the other countries to know which policies to enact, for example? My best answer would be, do not use data. Just see what works, what doesn't work, and try to do as much as possible of copying what works and as little as possible of copying what doesn't work. This is a kind of analysis which it's very common sense. It has a name. I call it bright spot analysis and dark spot analysis. So bright spot analysis is look at what works and try to reproduce it. And dark spot analysis is look at what is not working and try to do as little as possible of it. And you can use it in different contexts, even in your life. For example, if you see that you are supposed to write a report each of the previous 5 days, and you've seen that on Wednesday you were exceptionally productive, then Wednesday is your bright spot. And the good question for you is, what were the conditions that took place on Wednesday, and how can I extend them as much as possible to my week, to my next week? Or the same thing is dark spot analysis. So if you see that on Tuesday you were especially unproductive, then the good question is, what were the conditions that took place on Tuesday that made me unproductive, and what measures can I take today to make sure that those conditions will not apply to me next week? And that's an analysis that I would like more countries to make, especially now that we have a lot of examples. We can copy from South Korea, we can copy from Italy, we can copy from different countries with different outcomes. Okay, another question. Can we create an open document and a campaign for volunteers to add data to the table worldwide to establish better data points? So what I will do is that there is already this group of volunteers at endcoronavirus.org. I'm there as well in the Slack. I didn't take an active role so much up to this moment. I think that maybe what I will do is that tomorrow I will try to coordinate with them, and then we will find either we find a solution with them inside their project, or otherwise I will create an open document on my side, and anyway I will post on Twitter over, let's say, by Tuesday, or some way forward, so that people can contribute worldwide and we can establish good data points worldwide. Another question, what about serology rapid tests in addition to temperature? Has that been done? So I know that there are countries that have been using serology at least partially, for example, Singapore. I do not know the extent to which they did it. To my knowledge, to my limited knowledge, no country did it so far on the world population. That's definitely something which would be good to do, if possible. I do not know how hard it is to source those tests. But yeah, it's definitely important to have some tests that you can use on larger scale. Another question, a good test must have a high sensitivity and high specificity to reduce false negative and false positive respectively. To make a really good test is hard in this time. How can a country handle this? So two things. So the thing is, if you do not know how good your tests are, so first thing is test them before you begin using them on the large population, or use them but but always err on the side of they might be wrong unless proved otherwise. And the second question is, try to adopt policies which are resistant to erroneous testing or that do not really need tests. So that's why I was a big proponent of let's begin social distancing and let's begin closing borders before we test people, for example. The whole idea of this approach is we have tail risks, the epidemics. We cannot afford mistakes. So whenever we know that there is something which might lead to mistakes, then protect first and measure and model second. Then another question, wouldn't a lower sensitivity test work? Especially one that can also find asymptomatics and convalescents. I'm just finishing to read. Looking at. Yeah, okay, so this links back to the previous question. The idea is that the first most important parameter is to make sure that the actions that you will take based on the outcome of the test will decrease global risks rather than increasing it. Once you make sure of this point, then you can proceed. So this is the compass that you should use whenever you collect data, whenever you build a model, whenever you test. It's that given the uncertainties, you make sure that the actions that you will take on the outcome, they decrease the overall risks on the system. That's basically the concept that the compass that you want to use to guide your decisions. I check if there is any more questions on Twitter. Okay, since there are no more questions, so thank you very much for joining. I apologize again for the power cut. I will try to upload the recording on YouTube over the next days, and then I will post on Twitter once it's done. One thing I would love is if you can comment back on the original tweet with the invitation to this call, with some feedback, with additional question, or whether you find it useful or not, because it could help other people. I can use it for organizing other calls in the future and to get more people to join. And yeah, thank you very much. And then if there is any question, I'm always on Twitter. Thank you. Bye.